In this video, we're going to solve some problems in which we define what type of hybridization is present on an element in a molecular formula. Okay, we're also going to decide whether the molecule is bent, linear, or tetrahedral. So our approach is going to be to first draw a loose structure. We need to know how many covalent bonds or ionic bonds are in that structure. And we also need to count the number of non-bonding or lone pairs on the indicated atom that we're studying. We should know that the total number of electron pairs on that atom in the molecule is equal to its number of bonds plus the number of non-bonding lone pairs on it. And for hybridization, this is our template that tells us what type of hybridization is on an atom in a molecule. An atom that has sp hybridization only contains two orbitals. And remember, when we combine an s and a p orbital, we get an sp orbital, and we end up with the same number of hybrid orbitals too as atomic orbitals that we started with. These orbitals are always in a linear fashion. So this would be the central atom right here, the atom of interest, say X here. One bond goes to the right, the other bond goes to the left. Okay. Now, I'm not going to ask you to draw these complicated lobes on a test. Basically, you need to tell me whether that bond is sp or not. If there's just two, it's sp. If there turns out to be three bonds in a molecule and no lone pairs, that's going to be sp2 hybridization. We start with an s, we mix in 2p atomic orbitals. We end up with sp2. We start out with three atomic orbitals. We end up with three sp2 orbitals. They're oriented in type of a triangular fashion. So the central atom is right here in the middle. So one bond, two bond, three bonds. 360 degrees in a circle, so each bond angle is 120 degrees. If we combine an S plus three P's, Px, Py, and Pz, we end up with sp3 hybridizations. Since we're mixing four atomic orbitals, we end up with four sp3 orbitals. They're always oriented in a tetrahedral configuration. In other words, this is called a tetrahedral configuration because if we actually join all these points together, we get a tetrahedron, which is a four-sided polyhedron. Okay. Now the bond angles for sp are linear, 180, sp2, 120, and for sp3, more of a complicated 3D configuration. Each bond angle is 109.5 degrees. Okay. So let's look at a problem here. Find the hybridization on magnesium in MgCl2. We also want to know whether this molecule is linear, in other words, whether we have something that looks like this or whether it's bent like that. Okay. All right, so we'll start by understanding this is an ionic compound. We're going to draw its loose structure. So we go to the group numbers for these elements. Magnesium is group 2A, two valence electrons that form bonds, and chlorine, a halogen, has 7 valence electrons. So what we can do is we can actually pair up the single electrons to make bonds. In this particular case, because this is going to be an ionic bond, a chlorine is going to transfer its electron. In this particular case, the magnesium is going to transfer its electron to a chlorine, and that's actually going to happen twice. Okay. We'll end up with two chloride ions, each with a -1 charge, and a +2 magnesium. This whole structure is held together by electrostatic forces of attraction. To show that these chlorides have complete ownership of the octet of electrons, including the one electron transfer from magnesium, we put the chlorine and its electrons in square brackets and put the negative charge out front. So this would be an ionic bonded structure for it. It can only be linear or bent. Okay. We look at the atom of interest, which is magnesium right here. It doesn't have any lone pairs on it. It has two bonding pairs of electrons, one to the left, one to the right. So since there's only two bonds here, the only type of bonding, type of hybridization that fits this, or two bonds, two orbitals, is sp. So the magnesium is sp hybridized, okay, right there. And it's got to be linear because sp hybridization is linear. But if you think about this, there aren't any lone pairs on this magnesium here. The electrons to the left and to the right of the magnesium want to be as far apart from each other as possible. That can only happen if everything is in a linear configuration. So our chlorine, magnesium, chlorine bond angle is 180 degrees. Our second example is H2S, okay, and we're interested in the sulfur, its hybridization. We're also interested in trying to figure out whether this molecule is linear or bent. So we start out with the loose symbols for the indicated atoms here. Sulfur is in group 6A. It has 6 valence electrons. The molecule is going to have one of these two structures, either linear or bent. We can figure out which is which by finding the hybridization on the sulfur. If it's sp hybridized, then it's linear. If it's a higher type of hybridization, then it's going to be bent. Here's our loose structure to start with. You've seen this type of thing before. We look at our sulfur and we count the number of non-bonding electron pairs, which is going to be 2. The number of bonding pairs, we have 2 SH single bonds. So we have 2 bonding pairs. The total number of electron pairs, both bonding and non-bonding, on the sulfur is going to be 4. So if we go back to our table here for hybridization, the only choice that we have for containing 4 different orbitals is sp3 hybridized. So when we have hybridization, okay, we're counting both non-bonding and bonding electrons. So in SH2, 2 of these orbitals here aren't really bonds, they're non-bonding, but they still take up this tetrahedral configuration. 2 are non-bonding, there's our sulfur, and 2 are bonding. Okay. So sulfur is sp3 hybridized. The structure is going to be tetrahedral, okay, overall tetrahedral. But this is really the molecule that we have here, HSH. In the final structure, we usually don't show these electrons in an orbital there. So our final structure is bent. So I've shown that here. Sulfur is sp3 hybridized. The H bond angle should be 180 degrees, but the electrons in these orbitals here push those H's in. So the final bond angle is actually going to be less than 109.5 degrees. And this would actually be a structural formula for this, like a loose formula, showing the bent configuration, okay? Here we're just showing the electron pairs as dots, not in their tetrahedral conformation. Next example is ammonia NH3. We want to know the molecular shape of this molecule, and we want the hybridization on the nitrogen. So we start with its loose structure, which we've seen before. The number of non-bonding electron pairs is 1. The number of bonding electron pairs is 1, 2, 3. We have 4 total electron pairs. Again, the only configuration hybridization that actually matches this is sp3. Okay, so our nitrogen is going to be sp3 hybridized. We actually have 4 orbitals. 3 of these are bonding orbitals having NH bonds, and 1 is an orbital that just contains a lone pair of electrons. The overall structure of everything is tetrahedral, but really that's not the molecular shape because electron pairs don't count in the final shape because there isn't any nucleus on that lone pair. Okay, so this would be a final structural formula for that. If you look at this, it actually looks like it's pyramidal, trigonal, triangle base, okay, kind of like a pyramid. And that HNH bond angle is predicted to be 109.5 degrees, but this lone pair of electrons is going to push those H's away. Think of this lone pair of electrons. It's in an orbital. It takes up a lot of space, and it's going to take up a lot more space than if there were another positive nucleus here. If there were a positive nucleus up here, it would kind of rein in everything, pull everything in. There isn't any positive nucleus up there, so that's going to take up a lot of space and repel away the electrons in these NH bonds. That's going to change the bond angle here, the HNH bond angle, to be less than 109.5 degrees. My last example is BH3. We want the hybridization on the boron, and we want the shape of this molecule. So we'll start with a loose structure, which looks like this. Boron is in group 3A. It only has 3 valence electrons. As we saw before, this molecule violates the octet rule, but it is stable. We count the number of non-bonding electron pairs on boron. That's going to be 0. The number of bonding electron pairs is going to be 3. The total number of electron pairs is 0 plus 3, or 3. We go back to our table here. The only type of hybridization that matches 3 orbitals or 3 electron pairs is sp2 hybridization. Okay, so we figure that the boron here is going to be sp2 hybridized. That's a triangular shape. So we've drawn the 3 BH bonds at bond angles of 120 degrees there. Okay, and the overall structure is trigonal, triangular, but planar. Everything is in one plane. So that's how we use hybridization. Okay, if we actually looked at this from the viewpoint of MO theory, each of these BH bonds would be a sigma bond. Okay, in fact, for the NH3 molecule, we don't have any double bonds, so every one of these is going to be sigma as well. And for the SH2, no double bonds, so these are sigma bonds. So that's it for this video.